Okay, today we are going to attempt a rather ambitious topic. And it's ambitious because a lot of people find machine learning very puzzling, very confusing. But today I'm hoping to teach you enough about machine learning that when someone uses it, you're able to put it in context and have some beginning of understanding what has been done on your behalf. Okay? So, do I expect that after today's lecture you're ready to do machine learning training on your own hook? No. But I would like you to be able to understand the concepts of machine learning so that if you do end up interacting with someone to create a machine learning based classifier, you'll understand the basics of how that works. Now, I note that I've made my title Machine Learning / Statistical Learning. And that is because there are a lot of methods that sort of fall on this boundary between machine learning, which more or less comes out of computer science, and statistical learning, which comes out of biostatistics. So we have this sort of boundary, and it moves back and forth all the time. There are some topics like linear discriminant analysis that bear an awful lot of similarity to this classification, this classifier-based strategy. There are techniques. There are a huge number of terms that come out of the machine learning space that abut this. So I don't want to say right where the boundary lies between the two, but a lot of the concepts apply between both. So as we move through the lecture, I think you're going to see more and more ways in which machine learning applies in the context of biomarkers. It's quite rarely the case that someone produces a signature from biomarkers without resorting to machine learning. So we're going to talk specifically about supervised machine learning. And along those terms, we're going to talk about training sets, validation sets, and testing sets. We're going to talk about a couple big challenges that show up all the time where machine learning is involved. These are terms overfitting and signal leakage. We'll try to talk about how these things happen. And along the way, we're going to talk about the architecture of different systems people use in order to achieve a supervised classifier. So they might use decision trees or random forests, artificial neural networks, and support vector machines. And all of these require some explanation and a walk through how they do their thing. So I'm going to try to do that. But largely we're going to be talking about the conversation we have around supervised machine learning. So let's start with this distinction between supervised and unsupervised learning. Okay? Now, I've pulled a lot of this from this blog post, and I thought that he had one of the most succinct explanations to work with on what supervised and unsupervised machine learning represent. So at this top we see supervised learning is useful in cases where a property, a label's an important term to have certainly, is available for a certain data set. It's a training set in this case. But in other instances, those labels are missing. So I talk a lot about tuberculosis. It's a fine place to start. So in a supervised learning set, a supervised learning strategy, you may have a big data set of metrics you've produced from some population of people. And for that population, you know that this person has TB, this person does not have TB, this person does, this person does, this person doesn't, this person doesn't, right? Those are labels that we can apply to these different vectors of information that we have on individuals. So in this case, we have labels for this training set. But ultimately, the application of this learned classifier is that we can go to somebody we don't know the status of. We don't know if this person has TB or not. We want the machine learning system to be able to make a judgment on yes, this person does, or no, this person does not have TB, based on whether the metrics we can measure for that person are more like one group or the other in the training set. So these labels are a really key thing. For a training set, they're essential in supervised learning because we're going to use those labels to learn what people with tuberculosis look like in terms of the metrics we can compute for them. All right, now unsupervised learning is useful in cases where the challenge is to discover implicit relationships in a given unlabeled data set. In other words, the items are not pre-assigned. So imagine that you had some things like, what is the largest occlusion in this person's lungs based on a chest x-ray? You had their current temperature. You had maybe their lung tidal volume, how much air they can breathe in and out with each breath. You had these different metrics for somebody, but you don't know, in this case, which of the people you're being presented with do have TB and don't have TB. You just want to see, can I group together the patients for which we have this information in some way that says, look, the patients you saw fall in 2 distinct clusters or 3 distinct clusters. That is an example of unsupervised learning, where you don't have a diagnosis to work with in producing this example. Now, I'm going to talk very, very briefly about unsupervised learning, but after this slide, we're done with unsupervised. Okay? Today's lecture is about supervised machine learning, and I just need to talk a little bit about what the alternatives are, because people use these alternatives a lot. So, I'm going to introduce to you hierarchical clustering and principal components analysis. Has everyone seen an example of at least one of these? Yes? A few people have. Okay. These techniques get used all over the place in biology. You don't have to be working in biomarkers for clustering or PCA to be important. So I want to talk about them very briefly. We start in hierarchical clustering with the notion that we can compute a distance between different people, right? So if you're sitting in this classroom, I can say how far is your chair from somebody else's chair by saying, okay, you're in row 1, position 3 for you, and row 2, position 3 for you, and row 2, position 2 for you, and I can compute a distance based on where you fit on these 2 axes. In the same way, even if you've measured 100 different things for each patient, you can compute a distance in the space comprising those metrics. So maybe you have a bunch of temperatures. What is the body temperature of each of the person who came to the clinic? And you also have a BMI. Does everyone know what BMI is? Body mass index. So basically how heavy they are, what their circumference is, stuff like that. So these are just numbers. Now we don't think of these numbers as X and Y values, but you could easily imagine, I think, that if we had the BMI on one axis and the core temperature on another axis, you could plot all of the different people that came to the clinic that day. So in the same way, even if you've got 100 different metrics, you can create a coordinate space in which all these people fit. And you can say, what is the distance between any pair of them? So distance metric is a really key thing for hierarchical clustering, because it's the way of figuring out who's like somebody else in this space. So we then have some methods that are called agglomerative or divisive techniques. And these techniques allow us to build what's called a dendogram. This is a dendogram down here. You see that we have A and B and C and D and E and F. In this case, the software has decided E and F are most similar. It decided A and B are the next most similar. After that, it decided that D was most like this union of E and F. And you can keep going until you've built a dendogram that connects all of these together. This is an agglomerative approach. You can also imagine, I think, a divisive approach. In a divisive approach, you start with all of these data in this multiple coordinate space and say, where's the best place that I can lay a plane across this group of patients to separate things that are most like each other here and things that are most like each other there. And once you've done that, you then ask for this section of people that we've cut off from the rest, where can I lay a plane through them that will cut those into 2 groups? That's an example of divisive clustering approaches. Okay, so this is how hierarchical clustering works. You need to have some way to say how close are any 2 samples in the mix, and you need to have some method for going from that matrix of distances to a dendogram, and you end up with one of these. That's where they come from. Now, PCA, I think a lot of people use without really understanding how it works, and this lecture is not going to be long on detail on that either, I'm afraid. But I would point out that we're going to give a feature table, and we're going to spend a lot of time talking about features today. We're going to have a set of metrics that we've computed for each patient. Principal components principal component analysis returns components that are sorted by the amount of variance they explain. So principal component analysis is trying to show you what combination of the features that you're measuring for each person are best able to explain the variance that you see in the population. Principal components analysis does not know the labels that of the patients that you're feeding it. It just knows the measurements. And its job is to try to explain variability in the population, not to say, how does this class differ from this other class? That's a big misunderstanding a lot of people take into PCA. So in this case, we've measured sepal length and petal width and petal length and sepal width for a bunch of flowers, and we've used PCA to try to explain the variance in this population by just the first two components, those that explain the most variation. And then we labeled which ones were from which classes of plant. So this is PCA. So one of the very nice things about PCA is that it takes into account that some of the features you give may be correlated. For example, if I were to ask every person in this room, what is your height and what is your weight, we would probably find that the smallest person in the room, in terms of height, is not the heaviest, right? Instead, we tend to see that the people who are tallest tend to have the higher weights too. So that's an example of correlation in these two metrics. So the features that you give to PCA may be correlated, but the components that it returns are not. And this is a really valuable thing for dealing with shared information between metrics, like height and weight. Okay, so that's just a very brief overview of two very frequently used unsupervised methods. Now, let's turn to the kind of conversation we have with our computers when we're trying to do supervised learning. The computer scientist says to the computer, "Oh computer, I have measured these features on these subjects. Here is the table of these." All right? Now, what is the computer to do? Well, the computer's not ready to start yet, because for this to be supervised learning, we must provide labels for these. And in the next step, we see that. The computer scientist says to the computer, these patients all have TB. And then the computer scientist points to all the others and says, these other people, they do not have TB. This is the supervised aspect of it. So then the computer is asked, find a strategy to combine this information that we're providing about each patient, to combine information among all the different features that we're providing that will be able to discern the positives from the negatives. And this is where all the magic happens. We're going to talk about some of the methods used for accomplishing this last step, but I really want everyone to understand that in supervised learning, you must tell the computer which ones are positives and which ones are negatives in order that it can find the combination of features that best discriminate that call back and forth. Okay, on we go. So, there are several different tasks that we're trying to accomplish all at once. And to some extent, they're orthogonal, meaning that they're unrelated to each other, and in other cases, they kind of coordinate with each other. So these all came from a really great paper from Bill Noble's group in Nature Reviews Genetics. It's a good effort to try to explain supervised learning to somebody who doesn't know much about it to begin with. So there are these three goals that are kind of at right angles to each other. The first, identify a small set of features that yield the best possible classifier. So maybe you're giving the software 5,000 different genes that you think might be important in deciding who has TB and who doesn't, right? How much gene expression do we have for each of 5,000 genes or 10,000 genes? This is one of the common uses that we give to supervised learners. But we don't want the software to use 5,000 features in making this determination of what separates a positive from a negative. We really want it to sift through that great mass of genes and pick a small number, maybe 10, maybe 50, something like that, that are all we really need to make the best decisions of which folks are positive and which are negatives. So this is something that we call feature selection. This shows up all the time. So finding that which of many features we offer that are most valuable in making the decision is this feature selection problem. The next one, use the classifier to understand the underlying biology. All right, now if we were to use a massive table of features, everything about the person from his or her credit rating to how much he owes in student loans and so on, some of these, there's a lot of information possible about an individual, but there's an awful lot of it that we think of as unrelated to that clinical decision. If I gave you a machine learning output that said, all I need to know in order to evaluate whether someone has tuberculosis or not is the value of the car they drive and their grade point average, would you find that compelling? You would not. What if I told you that the tidal volume of their lungs and their current body temperature was useful in understanding whether or not somebody has TB? You feel that's a little more compelling. So ultimately, as biologists, and biotechnologists are biologists certainly, we're going to be concerned about whether or not the machine learner that results is in fact interpretable in terms of the biology of the disease. If I were to give you back a result that says, if you live in an area code, an area of Cape Town that has very dense housing, that has limited access to air conditioning, and that you probably eat fewer calories than other folks, that would also be true, right? And yet, from a biological perspective, it doesn't tell us a whole lot of very precise information. So when we create these classifiers, we're quite frequently trying to learn about the biology of the disease, not just how to detect who does and does not have TB. All right. Finally, train the most accurate classifier. And this is the thing where the computer scientists pump a fist in the air and say, yeah, right? We talked about sensitivity, we talked about specificity. Accuracy is this close cousin of the two. So if all you're trying to do is maximize your sensitivity and specificity in detecting people with TB and calling clear people who don't have TB, you're only asking the question about accuracy. So you can see that all three of these goals are sort of orthogonal. We're trying to figure out which subset of the information we provide is useful. We're trying to understand something new about the biology of the disease, and we're trying to accomplish something statistical in terms of what accuracy we can deliver with this classifier. Okay, so let's talk then about feature vectors. Now, I spend a lot of time talking about TB, but for just one slide, I would like to talk about the disease that haunts my family, diabetes. You see, my family has a sweet tooth, and if you put a bag of jelly beans in front of me, it won't last long. So we have to be really careful as we get older and a little more rotund in our middle-aged years that we don't develop diabetes from these very, very bad habits. So let us talk then about what information you need to decide whether Professor Tabb has diabetes. So here we have a patient ID. Now, first off, I have to fault the person who created this patient ID because this patient ID is my initials followed by 001. That's lame. This gives away my identity very, very easily. So I do not like this patient ID. But we'll just move on. I'm going to get over it. Now, temperature. Now, to me, my temperature is 98.6 degrees because I think in Fahrenheit. So I used Google to tell me that that's 37 degrees Celsius. We okay with that one? Okay. Next, BP. Does that mean I shop at British Petroleum? No. Blood pressure. 120 millimeters of mercury systolic and 80 millimeters of mercury diastolic. How am I doing so far? My physiology holding up? This is good. All right. HbA1c. HbA1c. Does anyone know what that is? Okay, if you're a diabetic, this number rules your life in a lot of respects, because this refers to how sugary your hemoglobin is. That's a very, very bad explanation of it. But this number is one of these things that people always worry about, is has your blood sugar been too high recently, is another way to look at this. The body mass index, 26.2, and the blood glucose, 5.3 millimolar per liter. Okay, so these are metrics that are relevant to whether or not I have diabetes. So this is a feature vector. Each of these is a different feature for this particular patient. All right? Those aren't real numbers, by the way, I just made this up. So I'm not giving away any personal information on what my actual blood picture is. Okay, so this is a vector, meaning just a row of information. And I wanted to point out that we have different data types represented here. In fact, one of these, I craftily snuck in 2 features within one column. Did you see that? The systolic and diastolic blood pressures are actually separate features, but here I've glommed them together. That's cheating. So we have integers, meaning they might be counts of things. We have floating point numbers, like 26.2, the floating point within it. And values from a set are also possible. What if we put my sex on here, right? We could put I am male or I am female. That's 2 different values drawn from this set, right? So that kind of factor variable is also possible. Sometimes values are missing. So if you are doing measurements in the field and somebody has to rush off halfway through their appointment, you're not going to have a complete vector of information for that person. That's problematic. Now, I'm not going to get into things like imputation, but imputation is one of these processes that we use to try to fill in fields that are missing for a patient. Okay, now, feature selection. The curse of high dimensionality. We work in biotechnology, and that probably means that we're using something like a mass spectrometer, or we're using a sequencer, or we're using a microarray, something like that, to make lots and lots of measurements from an individual sample. This, however, leads to a really ugly situation. As the number of features grows, more observations are needed to figure out which of those features actually matter. So the longer the list of information you provide about each patient, the more patients you're going to need to figure out which ones matter. Biomarker feature sets typically outnumber observations by 10 or even 1,000-fold. Shocking, isn't it? So let us imagine that we are working with a microarray and we're measuring 20,000 different transcripts for a person. How many patients would we need to have only 10 genes per patient in this study? We're measuring 20,000 transcripts. How do we get to 10 to 1? How many patients do we need? You divide by 10. You'd need 2,000 patients. So how many of us are about to do a 2,000 patient microarray study? Not bloody likely. It's a pretty rare study that can get enough money together for that many people. So we see that the number of features we're offering is very large compared to the number of patients we actually have. This is a recipe for overfitting. And here comes the definition. Overfitting produces a model that gives a seemingly perfect separation, a perfect classification of our patients, but it will not generalize. All right, so we can create a model from our training set, and it looks great. But when you start giving it new patients, the results are pants. They're just terrible. This is an example of overfitting. Okay, so for this, we frequently make use of techniques like feature selection. So we can score each of the features we have separately, figure out which of those are actually useful in making this determination, and then only let the classifier see the best of them. That's one way to deal with this. The other possibility is that you can add or remove features iteratively. So you could do something like this. Tell the machine learning algorithm that I want you to pick the single gene that gives me the best separation into positives and negatives. You only get one gene out of the 5,000 or 10,000 I'm presenting to you. Next, I could say, now machine learner, you get 2 genes to work from. You can pick any 2 genes that allow you to make a decision into positive or negative. And then you ask, Does its discrimination improve? How much does it improve? If you go to the 6th gene or the 7th gene, does your discrimination improve just very, very, very slightly? Well, then you probably don't need that extra gene added in. And you can also do this to remove them. You might originally put together a biomarker panel of 10 things you want to measure to separate into positives and negatives, and later you realize, well, actually just 8 of these are doing all the work. I'll throw out the other 2. So this is one of the ways in which feature selection helps us to tune the result of machine learning. All right, so let us now talk about training sets, validation sets, and test sets. So we start with the fact that we're not going to give the machine learner all of the data and say, make the best learner you can from that. Because we would have no external way of evaluating, of putting it on a scorecard to say, this was a good learner or this was a bad learner. So what we must do is to separate 3 ways. We have things that, labeled cases that the software is going to use to develop the classifier to begin with. And then we have another set, also with labels, that we can score this learner against. And then we have a separate data set. We've partitioned all these items out. And only when we're absolutely ready to publish do we take the validated model that's come from this and apply it in this test set. We only get to use it once. Because once our machine learner has seen what that test set looks like, we don't get to use it again. So, in this first set, the training set is going to be used for feature selection to figure out which of the features are actually useful in making a decision. And it's going to come up with a decision rule to be able to say anything higher than this is a positive, anything lower than that is a negative. It's exactly the same thing as the horizontal line that we drew in the 3rd column on the Tuesday lecture about receiver operating characteristic curves. Okay, so we're asking the software which features matter and how do we come up with a decision on an individual patient. We can pass that through other data that this learner has not seen in order to validate that model in this context. And then when we're ready to publish it, maybe we do a little bit of tuning back and forth here. Maybe we did, we had a 10 gene model and we decided we want a little better discrimination, so we went up to 12 genes. So we ran through this validation process twice, and then only when we have something that we're ready to put in the can and say this is done, we then apply it to the test set to show how well those rules generalize to these other examples. Okay? So everybody should have clear in their minds that a training set is useful for us in creating the model to begin with. The validation set is used for us to decide whether this individual learner is any good or not. And finally, we apply in the test set just that very last time to get the data by which we represent this model for new data. Okay? So, some people shuffle things around a little bit. So, we've already mentioned that we're going to do a training and test split. These data are only going to be used once. This is just another way to visualize what we were looking at a moment ago. But sometimes people are going to evaluate the variability of models derived from training data in a kind of unusual way. This is called a 5-fold cross-validation. Sometimes you'll see something called leave one out cross-validation, which is even more extreme version of this. But for now, I want you to imagine that all of these training data can be carved up into 20%. You have the first 20%, the second 20%, the third 20%, the fourth and the fifth 20%. So these quintiles, that's the technical term for them, are going to lead to us creating 5 different models from the same training set. So we train a model on the first 80%, on the first 60%, and the last 20%. The first, sorry, I'm not keeping this straight in my mind, but you can see that we're changing each time which part of the training set we're using and which ones get the validation label. So we get 5 different models out of this, and we can evaluate what was their median performance when we look at across all 5 examples, because that might give us a more typical representation of how we're doing. So 5-fold cross-validation still doesn't violate the rule that the test set gets used only once. but it does alter whether individual members are part of the training set or the test set for any particular model trained from it. How are we doing? Is this making any sense? Some? Some. Would this be a good moment for a question? Not yet? Okay. Well, keep me accountable on this. This material is tough. I was kind of frightened of this lecture. I needed to teach myself a lot of things to try to get the most tractable pieces of this to you. So I hope this is useful. All right. So you know I use a lot of religious imagery in my lectures, and I've done it again. Here I have the 6 commandments of machine learning. Number 1, thou shalt not represent thy model's performance using the validation set. Okay, so how does this work? If you're a computer scientist, you know that the best performance you can produce on the validation set is something you can game a little bit, right? You might try any of 20 different approaches to derive from the training set something that validates really well, and you keep just the one that does best on the validation set. If you then use the validation set result to describe how well your learner works, you're cheating, is what you're doing. So it's only this exposure to the final test set that gives us something that we can publish and say, this is how this model performs on data it's never seen before. Number 2, thou shalt not overfit thy model. So if you have 20,000 transcripts that you've measured quantities for each patient, if you allow the software to use all 20,000 of those features in order to produce a model, it's going to have something that is very strongly overfit to all of the oddities of each training set. So it's really quite dangerous to do this. Ultimately, a good supervised learner is useful in new data, not just in the validation set. So we must not overfit. Next. Thou shalt not generalize outside thy scope. Now that might seem a little odd, but look, what if I create a signature that helps me decide, let's say, household contacts, right? So we use the term household contacts a lot in TB to describe the people who live in the same home as somebody who has TB, right? Household contact. So one of the things we want to do is figure out who, living in a house, is more likely to pick up TB from somebody who's living with them, right? Just as an obvious thing, if you are living with the HIV infection, you're more likely to be susceptible to a TB infection. So that's kind of a gimme. But among people who don't have HIV infection, is it possible to determine which of them are most at risk and which of them are least at risk? Okay, so imagine that I develop a great model for household contacts of TB. Is it then appropriate to use that model to evaluate whether which people in a particular elementary school are, which of the learners in a particular elementary school are most likely to contract TB? That's pretty iffy, isn't it? These are very different clinical scenarios. Therefore, we need to be careful that when we create a supervised learner, we remember where it was trained and that its purpose is for this particular clinical situation. All right. Thou shalt scrub thy input of signal leakage. Now, I haven't defined that yet, but I'm going to come back in a slide or two and we'll cover that one. Basically, you should not let your machine learner look up the answer in the back of the book as it's training itself. That's bad. All right. Thou shalt expect model instability. You remember just a moment ago we were talking about fivefold cross-validation. In that case, just changing which 20% of the data served as the validation set resulted in 5 different models all drawn from the same training set. So something like that tells us that when we do machine learning on multiple slices of the data, we can expect that the models that result, the classifiers that come from that, are going to vary slightly. And understanding the extent of that variation is very useful. And finally, thou shalt not use machine learning uncritically. This is a hard one to explain well, I think, but I would say that people often say, the computer says this, therefore it's gospel truth. That's a dangerous perspective to take. Computers make mistakes because people like me write software for them, and I am certainly flawed. There's no programmer alive who hasn't written a bug or two. So I have to caution you that just because the machine learning algorithm says these genes are the ones that I'm using to make this decision does not mean that those genes are the only ones that could possibly be of any significance in understanding that decision. Okay? So anytime we see a result from machine learning, we shouldn't say, oh, it's from machine learning. It's part of the fourth industrial revolution. It must be the best possible answer. We should not fall into that trap. Computers are fallible because they are programmed by people. Okay, on we go. So, overfitting. There was a slide on feature selection a few back that talked about creating a model that's tuned to the peculiarities of our data set that does not generalize well. That is a technical definition for what overfitting is. But what I want you to imagine is that our training set is how I slept last night. And I'm trying to find what is the best mattress I can make for a broad population of people. If my training set shows that last night I slept like this, and therefore we should always make mattresses in this shape, I've learned the wrong lesson. My training set is far too small to reflect all the variability of this population. Because I tell you, I didn't sleep like that a month ago. A month ago I was sleeping like this. Just because last night I was curled over on my side does not mean that that will always be true. And certainly if we broaden out our training set to a lot of people, this shape is not going to cut it, right? So this model of mattress does not generalize to Dave in multiple situations, not just how I slept last night. Okay? So, now I mentioned I was going to talk about signal leakage. And here we go with that. So signal leakage gives the model, this learner, information that lets it cheat. Cheat. Okay, so we had this feature vector before, but I've made an addition. Does everyone see it? Okay, now I'm including, again, false information about how much insulin I inject into my body every day. Now, the class label here, remember, was has diabetes, doesn't have diabetes. It's a very simple classification. This field is not called has diabetes, is it? It's called how much insulin does this person inject every day. But what do you know about somebody who injects insulin every day? They have diabetes. So it's perfectly specific. Not everybody who has diabetes injects insulin every day. But if you do inject insulin every day, you're bloody well diabetic. At least I can't think of a scenario where somebody would be doing this. So this is an example of signal leakage, because this field is perfectly correlated. Anybody with a non-zero insulin per day measurement can be judged to have diabetes. So that is an example of the label not appearing here, and yet the signal is still leaking through because this is included.
Wouldn't it help then? Wouldn't it help the machine to learn it though? Because then if many people with the same, so if now you have many patients and they all have similar numbers and they all have insulin per day, wouldn't the machine then be able to realize, okay, look, they all have similar high, like similar glucose levels or whatever, and they inject insulin, so therefore...
Okay, let me try to come at it a different way. Informing, one of the things we're asking the machine learning algorithm to do is to pick which fields matter in making a decision. In a case like this, it's quite likely to say, well, I don't really care about all this other stuff, but I know if they take insulin every day, they're diabetic. So it's likely to ignore information that's correlated with the condition, but not perfectly like this.
Makes sense.
Yeah. So we can't let those labels slip through and become part of the decision process. Of course, if you tell the software you can use the label field, which says diabetic or not diabetic, as part of your training set, that's a real problem, because then it can just ignore everything and pay attention only to the class label. So this acts as a proxy for, as a way that label creeps into the training information. Cool, good question. All right. So we're going to now talk about some of the mechanisms for machine learning, and this is not enough. It's not enough. I could do a whole semester course on this stuff, which would teach me a lot, but it would still not be enough to understand these things well. So we're going to try to walk through this at a fairly basic level in hopes that everybody can grasp some of this. So in this case, I want you to imagine that we have 30 patients separated equally into two categories of 15 people. And the 15 people who are positives, let's say, are blue, and the 15 people who are negatives are orange. Okay, so we have a metric that we can compute for these populations called impurity. So when we see that we have 15 blues and 15 oranges all mixed up together, we are maximizing the impurity that we can get for two classes of 15 instances each. We've mixed together two populations equally. This is as high as impurity can get with two classes. Now I want you to imagine that each of these 30 people has 3 measurements, or maybe more measurements as well. Maybe we have A through Z that have all been measured for each of these folks. We ask the software which of these A through Z values we've provided is most useful in separating blues from oranges. Okay? In this case, it says A. A is useful. If I can ask the question of each sample, is A bigger than 5 or is it less than 5? I can cut this population in 2. So let's call that our first rule. The software decides which of the features we've provided is most useful in making that decision. So the question will be, is A greater than 5? If so, you come over here. If not, you come over here. So you see, we started with 30 people, and this first question we asked dropped both of these populations down to 15 people. And what we see is that our impurity got a little better. You see that? The impurity over here was 0.44. The impurity over here is 0.44. But what do you notice about the color separation? Is it equal? Do we have the same numbers of blues and oranges? We don't. So up here we had 15 of each. Now we have 1, 2, 3, 4, 5 blues on the right against 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 oranges. So 2/3 of this population are orange, 1/3 is blue. Over here we have exactly the opposite. We have 10 blues and 5 oranges. So asking the question about just one feature gave us a start to separating these two populations. All good? At the next stage, we can ask the software again, given that we've already used A, what feature can we use to separate this pool even better into by color? And here it says, feature B is a pretty good choice. If that's below 7, I get this population. If it's 7 or higher, it comes into this collection. Now, how did we do? Did that work well? On the right, we have 1, 2, 3, 4 orange and 1 blue. On the left, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 blue and 1 orange. So, not terrible. Not terrible. By asking just 2 questions, we get to pretty homogeneous groups of people. On the other side, we ask what variable is most useful. And it's not guaranteed that asking a question about variable B is going to be the best way to cut up this population. Instead, it's feature C. And we see that over here, we have perfect impurity, a perfect impurity score. It's a completely homogeneous population. Maybe these are all negatives, I think we said. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, that's not all of them, is it? There's another one that snuck over here. So it's not a perfect separation in that we lost one of our negatives to this collection that's largely positive. So a decision tree is going to seek out those features that do the best at separating this population into increasingly pure sets of positives and negatives. Questions so far? Okay. Decision trees are a pretty robust technique that people have used for a very, very long time. And it's really machine learning that's transformed it into a real beast. we'll talk about on the next slide. But I want to point out that, so this is a term called Gini impurity that we're computing that tells us which of these outcomes is the best for a particular split. Now, I wanted to note that we could tell the software it's okay to just use another metric to cut up this one, to try to slice that orange off from all the blues, and this blue off from all the oranges, and this orange off from all the blues. You could do that. But what is likely to result from that is overfitting. Because the more steps you allow these decision trees to include, the greater the probability that you've forced it to create a model that won't generalize well. There's not a whole lot of impurity here left for you to slice away. Okay, so trying to limit the total branch length of a decision tree is useful in that exercise. All right, now here we have an example of lots and lots of these decision trees. We're using a technique called random forest. And random forest has become wildly popular as a machine learning technique, so it's really important that you know about it. I'm sorry, have I run too long? Are we? Okay, still doing right, good. So, in this case, we're using what's called an ensemble technique. So, an ensemble says that we have weak learners. These are learners that are pretty good, but they're not brilliant. And by combining the information of many weak learners, we're in a much better place. So we're going to try to create a strong learner by combining weak learners. So I want you to imagine that each of these trees, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We have 18 of them. Imagine that that 12 of the 18 say, this is a positive, it's somebody with TB. And that the other, I said 12, did I? That the other 6 are all saying this is not a person with TB. You might use a technique like voting to say, of the trees we have, 2/3 voted that this is a positive. Or 100% of them voted that this is a positive. Those are kind of different levels, different scores, weights that you would put on that kind of decision. So voting is one of the simplest ways to create an ensemble from a bunch of weak learners. Okay, but why would these decision trees differ from each other? That is kind of an odd thing. And the answer comes from a term called bagging, bootstrap aggregation. It's another term that I'm not going to get into a lot of depth on, but let's just start by saying that these decision trees differ from each other because they were given different information to develop the tree. We may have limited each tree so that it saw all of the features but from a different subsample. Or they might differ from each other because all of them, they all saw all the samples, but they saw different subcollections of the features that were available. But more generally, we see that each tree is trained on a different subset of the samples and on a different subset of the features. So because we've used different parts of the training data to train each of these trees, the trees differ in which features they think are most important to make the decision. Okay, so this approach has produced what's called the random forest, and the random forest is one of the approaches that we most frequently see used for making machine learning driven supervised learners from training data in biological applications. All right. Now, I think many people here have probably heard of artificial neural networks. You frequently see this term used in connection with the term artificial intelligence. And I'm going to talk a little bit about how they accomplish what they accomplish. So we start with the concept of a neuron. This neuron is not one from your brain, though. It's a data structure that we use for making decisions in computer science. So this neuron is going to receive two different bits of input. Maybe it's looking at the transcription level for gene 1 and the transcription level for gene 2, let's say. It then applies some weight to that value to say how important is it. So it might say, I really care about gene 1's transcription, but I care a little bit about gene 2's transcription. So it would have different weights to reflect how much each of those is given. And there's also a constant that we call the bias that steers it in one direction or the other. So it might be that irrespective of the information it's receiving on the inputs, it's just prone to giving a 1 as a positive result from the neuron. So you can see that we have a fair bit of configurability here. We have the ability to choose which inputs, which features are actually given as inputs. We have different weights to reflect how much it leans on one or the other to produce its decision. And it's got some constant that just says, how prone is this thing to saying yes anyway? Those are all configurable values. And the process of training an artificial neural network fixes these weights and the bias value so that it has the best possible result. So we don't just make our decisions on the basis of a single layer of these neurons. Instead, we want to have a whole lot of input nodes that are feeding their information to an internal hidden layer, and that hidden layer communicates with an output layer, which then gives its decision. That might seem sort of arcane and bizarre, and that's because it's a little arcane and bizarre if you ask me. But this is in fact how these things work. So how could something like this learn anything? And for that, I would talk about the concept of back propagation. Back propagation is one of the ways that we train artificial neural networks, like this structure right here, to make a right decision. So we can give it an example. We feed it an example's input values, the feature vector that we provided, and it comes up with a decision. And then we give this network a jolt, right? So if it makes the wrong decision, we kick it and say, that was not a very good answer. If it says, if it gives a correct result for this particular supervised process, then we give it a reward and say, hey, guys, you did a good job, you know? So we have this process in back propagation in which the label is used to reinforce or pull down a particular set of weightings. And by going through all of these different examples and giving it a kick or a carrot every time, we get a neural network that gives the best answers possible for this structure. If we go beyond that, this gets really arcane really fast, and I'm not qualified to talk about that stuff. But I hope that at least gives you some start of understanding why this is powerful. Now, recently, people have started using these networks in a way that is kind of surprising. In back propagation, we're encouraging or discouraging the network based on whether it came up with the right answer. In deep feed-forward networks, we don't. We don't tell it which are the right answers or the wrong answers. We assume that this neural network is going to figure out patterns in the data. So deep feed-forward networks represent another example of unsupervised learning, all the way back from slide number 3, I think. So deep feed-forward networks sometimes go under I think the trademark name deep learning. Has anyone heard of deep learning? Okay, well there was an article in Wired a couple years back that was a kind of, well, the headline is a little dismissive, but the short version was that researchers at Google created a deep feed-forward network and let it watch YouTube all day. We say that stuff will rot your brain, right? Well, in the case of the deep learning algorithm that was exposed to YouTube, the researchers noticed that after sampling millions and millions of videos off of YouTube, it started recognizing that some of these videos have features in common. And the dominant feature that it found in common was house cats. Yes, people like me who create videos of their cats and post them to YouTube have created a nexus of videos that all have our friendly furry felines appearing in them. And in this case, deep feed-forward networks were able to recognize that an awful lot of the videos on YouTube feature house cats. There you go. Artificial neural networks. The last one I'm going to talk about is support vector machines. SVM is a very widely used method. It's probably the most closely related to statistical learning that we're covering in today's lecture. Now, I would ask you to look at this data set at the upper right. Everyone sees that. I don't know if this is going to be problematic for folks who are colorblind, but you should see blue circles in the middle and red circles on the outskirts. So I would ask you, what line can I put across these data that separates all of the blue dots from all of the red crosses? She doesn't see one. Anyone see a way to draw that line? That's because we need to make a hoop, basically, to separate the insides from the outsides. And our software doesn't know how to do that. So, in support vector machines, we create something called a kernel function that gives us a way to look at which points are most similar. And sometimes we can allow these kernel functions to consider ways other than looking in a plane for these data. So if we use something, in this case, called a hypergeometric kernel, we can cause these data to be shaped like this instead, right? To basically fold the space it's in, and now we can cut a plane across there to separate all of the blues from all of the reds. So here we're distorting the space in which these exist to find where the best plane to cut the blues from the reds could be. Okay, so a hyperplane is a really important concept to get from this. The hyperplane reflects this slice that we're doing here. All support vector machines are trying to find an optimal hyperplane that chops the positives away from the negatives. And it ends up paying quite a lot of attention to these points that fall closest to where that hyperplane ends up being. So we can call those the support vectors to explain where the name of this comes from. So creating a support vector machine means finding the right kernel function that allows us to work with the data we have and finding the best place to position this hyperplane to separate the positives from the negatives. Okay. So hopefully, when someone says to you, artificial neural network, or decision tree, or random forest, you're going to have something to link that to. I hope that's useful to you. So, we spent a lot of time in today's lecture talking about supervised learning. Understanding how that differs from unsupervised learning is very valuable, I think. We're using labels to instruct the software what positives and negatives look like. All right. Many predictive models may be produced from the same input data. If we feed the same input data to a backpropagation network, to a random forest, and to a support vector machine, they're all going to come up with different models about separating the positives from the negatives. If you simply apply the same software multiple times to the same data set, you're likely to get different models out because some of these use random factors in trying to find the best separation they can. So the best models excel in a never-before-seen test set, not how they do on a reused validation set. Remember that for us, machine learning is always intended to create a model that generalizes, that can be used in new data where we don't know the labels. And for that, we must avoid overfitting. Okay, are there any questions from today's lecture? Okay, I realize this is a very advanced topic. Thank you for sitting through, and I hope that today you learned something that will be useful to you down the line. But with that, I'm done with lecturing for biomarkers. Caroline will be back here next Wednesday as things currently stand, but we'll keep you apprised as we try to figure out how to keep from interfering with Eid holiday. All right, have a great weekend, everybody.
You too.